All right, so this week we're going to start talking about colors. And we'll start off talking about artificial colors. And then we will talk about natural colors. Probably 5 or so years ago, this lecture would have, maybe half of it or 2/3 of it would have been on artificial colors. But now I just have a few slides on them. Has anybody noticed them kind of disappearing from products? Yeah? I know, like just last week, my kids, we got some, I have all girls, and so we got some Princess Goldfish crackers. And they're colored pink. And when I was a kid, probably they would have been this really pretty bright pink color. These were like super, really ugly pink color, and not really colored very well. I could still see like the yellow through it, and so this is the price that you pay for those, getting out those artificial colors. I think you can see it like in Fruit Loops. Definitely, they're just all like, the color is just really, really bad. So I like that because it really, we all remember what it was like when all those were there. And so it shows you the power of those artificial colors and how difficult it is to work with the natural colors. And so, we're gonna all be in that situation soon of having to work with those natural colors and trying to get the products, as attractive as they can be, but it is very challenging when trying to get out those artificial colors. So is this not going to let me? Okay. So first of all, all these colors, they're governed by different regulations. And those regulations are dependent on which country you're in. So in the US, all of the regulations for colors are in the Code of Federal Regulations, like all food rules in Title 21 happen to be in that section there. But in that section, it divides colors into certified colors, which are the artificial colors, the ones that have that FD and C prefix before them. And then exempt colors are the natural colors. And in the CFR, mostly, you'll notice there's not a lot of usage levels. So most of them, they just say, good manufacturing practices. So, use only as much color as you need, not more than that. And that's pretty much the regulations. It does specify which ones are allowed, though, but the actual levels are not so specified. That's in contrast to China, where the regulations there are in this document GB 2760. And in there, basically a lot of the same rules apply. A lot of the same color compounds are approved or not approved. But in there, it's very explicit about you can use this much, no more. You can use that much and no more in various products. So it's very prescribed in those regulations as opposed to in the US. And then in the EU, maybe something in the middle. So generally, it's a little bit less strict in the EU than in the US, but yeah, and if you see packages from there, they always have this E number, so that they'll have those E numbers for a lot of different things, basically all these additives, so colors, flavors, gums, all those different things. And so all these different colors will just have different E numbers that will be listed on the ingredient statement. So these 7 colors, the ones that actually have like a colored label under them. Those 7 are the ones that are approved in the US and the ones that are approved in most countries. The ones that are kind of on the border would be the green 3. So green 3 is actually the least used in this country. So I actually know of no color companies that will actually supply you this color. So typically if somebody requires green, they will just use a combination of yellow and blue. So very not common, and it's also not approved in a lot of other countries. It is approved in most EU countries. I have the E number there. Not approved in China. At least it's not on the list. The other one that's on the fence there is red 3. And that one is another one that we barely use anyway. That one's a little bit different than the green though, because there are a lot of countries where it's really popular. So, you know, it's probably not approved in a lot of countries, and then in other countries it's super popular. In the US it's approved, but it's not really used very much. Those colors that I made those boxes, those are representative of the actual color of those pigments. So you can see like that the yellows aren't the same hue of yellow, blues are not the same, the reds are not the same. And so, yeah, they are very different in their properties. Those 2 that are listed at the bottom, the citrus red and the orange bee, those are approved to be used, but only under certain circumstances. So the citrus red, as you know from the name, that is approved to color citrus peels, mostly orange peels. So a lot of times orange farmers will harvest oranges when they're still green. They'll still, you know, they make sure that the sugar concentration in those oranges is at a certain level, but oftentimes it will get to that level, but the orange itself is not orange yet. And so they can use that to color the peel of the orange. Yeah.
So why are the bees in red now?
Yeah, the green, well, I honestly don't know why the green is not really used. You know, I don't know of any safety concerns. I mean, it's approved. I don't know of any, but it's not, I just know that it's, I mean, I've tried to get it before because it's one of those colors that just passes right through you, unchanged. And, you know, kind of maybe I mentioned Fruit Loops earlier. So I don't know if any of you had this when you were little, but I know when I was little, eating Fruit Loops made my poop turn green. So anyway, I always assumed, oh, you know, it's those green Fruit Loops. And maybe it was. I mean, I was too little to notice what the ingredient statement was. But I have tried to get green, that fast green, for human trials that we have. So we can look at transit time. You know, basically you give them a green pill and then look for when the poop turns green, and that was how long it took to go through. And green 3 would be perfect for that because it's not metabolized, it's not absorbed at all, just goes right through. But blue 2 also has that property, so it goes right through, not absorbed. And actually, blue 2 turns your poop green also because of the brown in your poop, so it turns it green. So perhaps eating those Fruit Loops was actually the blue that I was seeing and not the green. But Yeah, I don't know exactly why. The red 3, you know, you can see the color is more pink. I don't know if maybe that has to do with why it's not very common. Like I said, it's really common in some other places though. So, but mostly here, if we want to color something red, it's red 40. Red 40 is almost always what's used, even if it's something that's pink. Here's solubility. They differ quite a bit in solubility. Not that this really matters, because you know, there are no products where you would ever want 1 gram of blue 2 in 100 mils of that product. That would be like, I mean, it'd almost be like tar or something that dark. So this is not really an issue at all, but they do differ quite a bit in their solubility. All of them, you know, I would classify as highly soluble. Here are the stabilities under different conditions. And so the length of that bar there is how stable it is and under those conditions. So you see, you know, the least stable one is blue 2. So those bars are the smallest there. And then maybe followed by red 3. Red 3 has, you know, no bar in a lot of those places. So, you know, that could be another reason maybe why it's not used, although that couldn't be an explanation for green 3, because green 3 is very, very good. You notice in alkali, some of these colors change. And, you know, but for foods, that's not usually something we worry about, because there's very few alkaline foods, and even fewer alkaline foods that actually have colors in them. But, and then at the far side, the right side of the graph, you see a bunch of specific compounds, and they can have reactions with these colors. Sulfites, ascorbic acid, and benzoates, you know, different preservatives. So artificial colors do have lots of advantages. They hardly cost anything and give potent color. They have high stability to processing and storage compared with natural color, as we talked about already. Very much more vibrant. And then you can also get them in water-soluble and water-insoluble forms. So we'll talk about what these water-insoluble forms are. They're called lakes. You guys have seen on labels, it'll say like FD&C, red 40 lake, or yellow 6 lake, something like that. So that lake is the insoluble form of that dye. And it's not like a hydrophobic version. So, you know, a lot of times we think insoluble, that means it's soluble in organic solvent, but actually this isn't soluble in organic solvent either. So it's basically not soluble anywhere in food. So what's the point of doing that? Why would you want to do that? So the reason is to basically color by dispersion rather than putting it in solution. So I can disperse this color in a food, and it will give me color, but I won't have, if I have like a multi-component food, I won't have some of that color bleed into the other component. So there's minimal bleeding. And also I can disperse that in anything, whether it's you know, aqueous-based food, water-based food, or a fat-based food. It will disperse in oil droplets and in water droplets that are present in the same food. And so that can give some good advantages. Oh, and it's also basically impervious to degradation because it's not in solution, it's not dissolved, so it's not going to be affected by pH, it's not going to be affected by heating, it's not going to be affected by, water activity, anything like that. So highly, highly stable. So they're produced by taking the colorant and precipitating it out on alumina, which is aluminum oxide. It's just like a mineral. And because of that, they're not going to be 100% of color. So a lot of that is going to be the alumina base, and so the color will range anywhere from 1 to 40% of what you actually put in the food. And idea is to get the smallest particle size because we're coloring by dispersing this color in that food. So a smaller particle size will do a better job of that. These lakes are they're more expensive, and you have to use about 10 times more of them to get the same kind of color effect. So it does cost quite a bit to do this, but you get all those other advantages of no bleeding, increased stability. One thing that you do want to understand, though, is the coloring strength. Since we're coloring by dispersion, adding more doesn't necessarily give you a proportional increase in the color that you see. So if you were coloring by dissolving it just with the regular color, if you add twice as much of that color, then the intensity of that color doubles. But it doesn't necessarily do that with the lakes, and it's a little bit less predictable about how you're going to perceive that color when you change the concentration. Okay, that's all on artificial colors. So we can talk about exempt colors. Most of these we would call natural colors, but using the term natural color doesn't apply to all of these natural colors. So one example would be that if we use beet juice to color strawberry ice cream or strawberry yogurt, which is really common, we can't say that it's naturally colored, even though it's a natural color that we're using. So we have to say, basically we just say something like beet juice color or colored with beet juice. But yeah, it's because, beet juice doesn't come in strawberry products. If we were going to sell strawberry juice, which is not something that is normally available, but if we were going to sell strawberry juice and we used a strawberry-based color to color that product, then we could say it was naturally colored, because the color that we're using came from the product that we're selling. So it's a little bit, I think, of a strange rule, but and that's what it is. So if you're using, a lot of these vegetable juices and fruit juices that we get these natural colors from, if you're using it to color a different type of product, then you can't put natural directly on there. It has to, you don't have to put artificial. You can, but you don't have to. But you can't necessarily put natural. This is just a list of all of these different things. You see, a lot of these are carotenoids. So like annatto extract, canthaxanthin, the beta-apo-8 prime carotenoid, beta-carotene, carrot oil, and these are all carotenoid based. So these are going to be yellows and oranges and reds. Also, they're going to be highly hydrophobic. So that's a problem, actually, especially, yeah, when you're coloring yellow or orange or red, we have some options that are water soluble, but certainly yellow, you commonly go to a carotenoid. But most foods are going to be water-based. So there are available water-soluble or water-dispersible carotenoid colorants. So, and they're simply a mixture of the carotenoid, beta-carotene, or whatever it is, and an emulsifier. And so, just like the lakes, those are not going to be 100% colorant. Actually, in a lot of cases, they're only 1% colorant and 99% emulsifier. And so you end up having to use a whole lot of those because, number one, the carotenoids aren't going to be as potent of colorants as the yellow 5 and 6. And then also, to get them water soluble, you put them with this emulsifier, and so now it's only 1% colorant. So before you were using 0.01% yellow 5, now you have to use 1%, 100 times more of the natural color, which is more expensive. So that's a challenging thing. You see here in the middle there, fruit juice, grape color extract, grape skin extract. So a lot of these are from fruits, different juices, vegetable juice here. So a lot of these colors are just coming from that, extracted with, different things. Generally, it would be a water extract. There are cases where you can use like ethanol or an organic solvent, but most often these are just water extracts and then concentrated or dried somehow to make the color. All right, natural, some specific natural colors now. So this is myoglobin. Myoglobin is the red color in blood and muscle tissue. Well, I should say hemoglobin is the red color in blood, but it has the heme there. That's what gives it the red color. So we've seen heme before. So right now, what you want to recognize is, yeah, this ring structure. I can never spell this. This is a porphyrin ring. It's called a porphyrin ring, very common type of ring. So we see the iron there, coordinated with those 4 nitrogen atoms in the ring. And then typically these, iron in particular, and all these metals really, they can generally coordinate with these ligands in 6 positions. So we see 4 there on the heme ring itself. And then one of them, like I mentioned, is attached actually to the protein. So attached here to the protein. And then 1 is attached to the ligand that the iron is attached to. So it could be oxygen, could be something else that we'll see in the next slide. Okay, good. That's all I really wanted to write in that box there. So, okay, so here are the different colors. So you see, basically, we see most of the time, we see red, brown, and pink. So those are the colors kind of that we most commonly see. We can get some defects, like if we get some sulfites, or more of a problem is that if we get some hydrogen peroxide on that meat, it can turn that pigment green, which is obviously going to cause all of that product to fail and not be able to be sold. But the hydrogen peroxide, why would that be such a issue? What's hydrogen peroxide going to be used for in a food plant? Cleaning. Yeah, good. So all of the equipment that you're making ground beef from or something like that, it's got to be cleaned. So you can use hydrogen peroxide to clean that. But if you don't rinse it, if you don't neutralize it somehow all the way off of that cleaning equipment, when you put that meat on it, it's all going to be ruined because it's going to turn green. But anyway, typically we see red, brown, and pink. So red is the desirable color for fresh meats. And so we want to preserve that red color as best we can. So we can keep that red color by having oxygen. You see, oxygen here is going to give it that red color. So, as soon as that animal is slaughtered and that myoglobin is exposed to oxygen, then it's going to have that nice red color. So that's fresh meat. As it ages, we mentioned before that that iron in the 2+ state can become oxidized to the 3+ state. So then what color is it going to change to? Brown. We see down here, if our iron 2 goes to iron 3, then we're going to have this brown color. And iron 3 can't bind oxygen, so we just replace it with a water molecule. But these two here would be like the matching versions. So this would be when that meat is fresh. If you let it sit out for too long, or you don't freeze it when you get home, keep it in the fridge for a week or two, then we get this met myoglobin. We can actually use carbon monoxide to keep that red color here. And that's actually like locks it in that position or locks it in that color. The carbon monoxide, carbon monoxide is super toxic, right? Because it binds that heme so tight that we can't get any oxygen anymore. And it does that in meat too. It binds it so tight that basically it will stay red forever till you cook it. And so would be really desirable, except it's not okay to do that. It's not approved to be doing that. So that's not something that we do. But in theory, it would keep that red color as long as you needed it to be red. Okay, and then so let's introduce this term called modified atmosphere packaging, which is abbreviated MAP. And so that's how a lot of meat is packaged. We package it so that we can keep the red color for as long as possible. And so modified atmosphere packaging is usually going to have elevated oxygen. So, kind of instead of 20% oxygen, it would be 30 or something higher than 20. To keep that oxygen there, or that oxymyoglobin for longer. And then, there's other gases there. This is just a filler gas, nitrogen. It's not going to do anything. It's just going to take it up to 100%. And then oftentimes there's some carbon dioxide, not monoxide. So oftentimes there's some carbon dioxide there as well, and that is not there for anything to do with the color. It's to control microbial growth. So typically those are the three gases that we can vary in lots of different ratios. So I'm not going to give you a particular ratio, but elevated in lots of different ratios to package these meats. Okay. Yes, and then when we cook the meats, you know, that iron is going to be oxidized. It's going to turn brown. So that's desirable once the meat is cooked, is that it turns brown. And then when we put nitrites on there, so that's the NO there, nitrites, that's what's going to turn it pink. Okay, next we'll talk about chlorophyll. So chlorophyll is a highly hydrophobic green pigment. I think that's not a surprise to anybody, but this is its structure. This is chlorophyll A. So plants usually have a majority of chlorophyll A, but they also have a significant amount of chlorophyll B, which differs here at this methyl group. That's why there's a box around it. B has like carboxylic acid group there. You don't have to really remember that, but this would be A and B would differ here. There's also C, which is in some bacteria, but not really in plants. Okay, so look at this ring. What does this ring remind you of? The one we just saw? Yeah, it's almost identical. You know, the only difference is this little extra ring down here. So this is very, very close to the heme, or to the porphyrin ring, except we have this down here. This ring is called a Forbin ring. So, and that's just because of this different thing down here. But we have, instead of iron here, we have magnesium in the middle. So these plant, or chlorophyll is going to have magnesium coordinated in that position. And if that magnesium comes out, the color is going to change, we would expect, right? If we put a different metal in there, maybe the color will change, maybe not. Let's find out. But anyway, and then this hydrophobic tail here, it's called a phytol tail. If we treat this chlorophyll with an enzyme called chlorophyllase, that's the part that comes off. So, oops. So here are the different colors that we can get of chlorophyll. So chlorophyll starts off green there, here. So this would be like the desirable color. When we start to heat that vegetable, beans or peas or whatever we're going to heat, what happens to the color at first? Does it get ugly, or does it initially get better? It gets better at first. So very, very short heating is actually going to intensify the green color. It's going to be more desirable. And you know, that's probably because of air within the cells, or the space between the cells being expelled because of the heating. And so that green color is going to be concentrated and intensify. So initially we get kind of a brighter green color. But after not too long, we start to get some negative reactions. So if we cook these vegetables for several minutes in water, then we can get that magnesium to come out of the ring. And when it comes out of the ring, that's what I'm showing here. This is minus magnesium. So it's come out of the ring. We get phaeophytin, which is an olive green color. And so not as desirable. Prolonged heating, and that's actually goes faster in acid. So if you put a little vinegar or any kind of acid in with the cooking water, then that discoloration will go faster. Prolonged heating, like if we were going to can these vegetables, then we get pyrophyophytin. And that's an even worse olive green color. And I don't know, on my screen, that pyrophyophytin is even worse of an olive green color. I don't know if you can see it very well there. But in that case, we lose that carboxymethyl group. And it's this one down here that comes off right here. But it's a worse olive green color. So we lose the magnesium and we lose that carboxymethyl group. If for some reason we lose the phytyl tail, we get thiophorbide, which is also olive green. All of these are just a really ugly green color. This phytyl tail, you see this is an ester linkage here. So it can come off at extremes of pH really, really easily. So if you are in acid, you know, that whole reaction is sped up a lot. The magnesium comes out and that phytyl tail can be taken off. So this ester linkage is very labile at extremes of pH. So we can lose that tail coming off. So that's what happens when we heat under normal conditions. Those are all normal conditions for, you know, cooking and preparing vegetables. And I'm sure all of us have seen those colors. But we can get some other things that we don't really often see. So one of them is, like I mentioned, just treating with chlorophyllase enzyme. And that will turn the product to a really light green color, chlorophyllide. We still have the magnesium in the ring, but the phytyl tail has been chopped off. And that is a naturally occurring enzyme, and it can start to do its job when the plant tissue has been sufficiently damaged or broken down. And then going the other way here, if we heat under alkaline conditions, then we get chlorophyllin, which is a bright green, very, very desirable color. So if you think about that intensifying color, when you first initially heat those vegetables, this would be like that, but you know, sort of prolonged. In this case, the phytyl tail comes off really fast because, you know, this ester linkage is unstable in acid, but basically it doesn't last at all in alkali. So it comes off very fast. And then we also can lose that methyl group up at the top. So we get that bright green color, very desirable color. So there was, you know, kind of a movement a long time ago now, but, you know, to do this, you know, to improve the color of these vegetables. But it doesn't actually do very good to the vegetable texture. So heating these in alkali makes the texture slimy and disgusting. And also, we've already learned that when we put a lot of vitamins in alkali, they degrade super fast. And, you know, why do we eat these vegetables but for their vitamin content? So kind of lose the point of eating them. So destroys texture and also vitamin content. And so it's, even though it makes them look really good, that's not really that desirable of a treatment to do. So you can actually preserve that green, bright green color in a safe and maybe more effective way. And that can be done by taking the magnesium out and putting in either zinc or copper. If you were to do that with copper, that would be illegal in this country. You can't do that here, but you can do it with zinc. So it's going to be more stable. It's going to give the products a brighter color and can be used even in canned products. So the way to do that is kind of I think a maybe non-intuitive way of doing that. And that would be, so first, you just put some kind of zinc salt in the blanching water. And I have some concentrations there. And then you're going to, make sure the pH is about what it normally would be. I mean, you probably don't have to adjust the pH at all, but somewhere between 4 and 6. And then you're going to heat up the tissue to pretty warm, 60 degrees. And you're going to hold it there for a while. And that's going to allow the tissue to soften and the magnesium to come out and the zinc to go in. So you have to do that before you heat, at really high temperatures. Otherwise, you're going to get the olive green color developing before you've had a chance to get the zinc in there. So preheat, get that zinc in there, and then you can do your, retorting or whatever you're going to do. So, this is not super common, but it is a way that you can preserve those colors a little bit better if that's really important. Okay, chlorophyll is highly susceptible to oxidation, but it is protected from oxidation in plant tissue. So in the plant itself, it's fine, and actually it's mostly going to be protected by carotenoids. And so here I'm showing chlorophyll and exposed to light, and it becomes excited chlorophyll. It's in an excited state, sort of ready to react with things. So if oxygen is present, then the chlorophyll will react with molecular oxygen and be calmed down. It will go back down to its regular state. But now oxygen here has become excited, this singlet oxygen, which is very reactive. So we don't want that around in our products. So carotenoids can be used. See here, carotenoids can become excited by reacting with excited chlorophyll. So the chlorophyll here, if it becomes excited from light, a carotenoid can come in and calm the chlorophyll down. And in the process, now the carotenoid is in an excited state, reactive state. And this time, though, that reactive carotenoid is now going to react with singlet oxygen, and then everything else is back to normal. So we have just a carotenoid here and oxygen. So everything's back to normal. So that would be what we want to have happen. But like, for instance, a lot of these oils that we use in cooking, they come from vegetables that have chlorophylls and carotenoids. And in the process of extracting those oils, these are really hydrophobic compounds, so they're going to come with the oil. And they are going to the carotenoids are going to degrade over time, and then the chlorophyll can go ahead and excite oxygen, and then the singlet oxygen here oxidizes lipids really fast. So we have to get rid of any of these types of compounds from oils when we're extracting them, because they will cause problems with storage. Five minutes. Okay, let's see. Maybe we can get through carotenoids. So these are some different carotenoids, some different structures that we maybe didn't see in the vitamins section. The point of this slide is to show you some of the characteristics of these structures that affect the color. So first of all, the color is a function of how many conjugated double bonds there are. Those are those numbers on the slide. So if we have phytofluene, which only has 5 conjugated double bonds, then actually there's no color. So we have to get a sufficient number here. This one has 7, and now we have some yellow color to that carotenoid. So first thing is the number of conjugated double bonds in the conjugated double bond system. So there's number 1, and you see here, these 3 structures, they're all the same except for how many conjugated double bonds there are. This one has 7, this one has 9, and this one has 11. And you see the color changes because of that. So we have yellow, and then going to orange, and then finally red. So number of conjugated double bonds. And then if we take lycopene here, that has 11 conjugated double bonds, and we wrap this end here into a ring, into that beta ionone ring, we get beta carotene, and the color changes again. So number of conjugated double bonds and presence of a ring or not is going to change the color. And then finally, the third thing is whether there's oxygen in that ring or not. So here, beta carotene and canthaxanthin are same structure except for that oxygen present in the ring. And again, now we change color here from orange to red because of the addition of that oxygen. So several different things change for these, and they're going to affect the color that we see. And so all of these carotenoids, they're going to go from yellow to orange to red, or colorless if they don't have any color at all. But generally, we look at the color ones, so these are going to range from yellow to red. So they're strongly lipophilic, like we can see in the structure. So they have to be dispersed in oil. But like I mentioned, most of the colors that you purchase are going to be water dispersible and mixed with a emulsifier. And yeah, a lot of these, they don't say carotenoids on them, but they're all carotenoid based, all of these that are listed here. I mentioned carotenoids are stable under most conditions when we talked about carotenoids in the vitamins section. They were traditionally regarded as stable to heating, but that's just because the color doesn't really change. So here, I didn't mention at all the orientation of the double bonds. So cis versus trans is not going to make a difference. So it's mostly just a number. Okay, I think we'll go ahead and end there. We'll start talking about anthocyanins next time. So. Well, there's someone